What's up people? I am Prachurja Biswas and this is the first Sciencation video. In this Sciencation video, we will discuss about the J.J. Thomson's cathode ray experiment, which I discussed nearly in the last atomic structure lecture. In the last atomic structure lecture, I told you that the J.J. Thomson cathode ray experiment is a bit little out of context, so we won't discuss that. But being a very interesting concept, I'd like to discuss in the Sciencation video. So this here, the man which is in the front of us is J.J. Thomson, who is considered to be the most pioneering scientist in the 19th century. In 1897, he discovered the electron for us, and thus we have the main particular nature of electricity and other beings. It is also important to understand the electron is a part of the atom. So this person here was the first to discover a subatomic particle for the atom. Now let's move on with the mathematical concept of the J.J. Thomson cathode ray experiment, which led to the discovery of electron. First of all, understand the J.J. Thomson's cathode ray experiment. It is important that you first understand the physical basics. For understanding the physical basics, there are two phenomena involving in the cathode ray experiment which are used to determine the E by M ratio of the electron. To understand this, we have first the electrical component and the magnetic component. For the electrical component, it is important to understand the forces applicable on the electrical component. The definition of the electric field intensity is the force experienced by unit charge kept in an electric field. That is, F is equal to E into E. Now if you understand the fact that what the various terms mean, then F is the force or the electric force applied or experienced by the object, E is the charge of the object, and capital E is the electric field intensity. You should need to understand that if force is a vector and charge is a scalar quantity, then electric field has to be a vector quantity. Similar is the case with the magnetic field intensity. In the magnetic field intensity, it is the force experienced by the charge force experienced by a unit charge when it moves in the magnetic field with a unit velocity. That is, F is equal to E into V into B. Now, F is the magnetic force experienced by the charge, E is the charge on the body, V is the velocity of the body, and capital B is the magnetic field intensity. But there is a slight twist in this kind of forces. You have to understand that F is a force vector, E is a scalar quantity, V is a vector quantity, and B is also a vector quantity. So, if V and B are both vector quantities, then there must be a specific relationship between them so that F is a vector quantity. Now, what actually happening here is that V and B being vector quantity, the F being a vector quantity, it has to be a cross product. So, V cross B will give us the direction of the F vector. So, what actually I am telling is, consider this that my tip of the finger is the arrowhead and this is the tail. So what is happening here is this is the V vector here. Like this is pointing in that direction towards you. I'm pointing towards you means the V vector is pointing towards you. And what I'm doing is I'll take a B vector like this. Okay. And this is the arrowhead. So if I have a B vector like this, right? It's something like this, right? If you can see it, it's something like this. Okay, so what I have to do is, in order to find direction, I will use the right hand corkscrew rule or rather right hand rule. In this, we need to curl our fingers in the direction of V into B. Like we have to move our fingers from V to B because it is V cross B. So what we'll do is, we'll curl our fingers in this direction because it is like this, right? I hold it like this and I curl the fingers in this direction. Then the thumb gives us the direction of the cross vector. So this is the direction of force vector. Similarly, if this was the V vector pointing towards you, the arrowhead is here, and I have this in this direction, like it is pointing in this direction, then I have to cross my vectors in this direction, therefore it will give us the upward direction. So the force vector is in the upward direction. So that is the meaning of the cross rule or the right hand rule. So what will happen here? So we have this photo here in which what is actually happening here. This is a cathode ray tube in which there is a cathode and an anode, a perforated anode. A perforated anode means an anode with a holes. And what is actually happening here is the cathode and anodes are connected to high voltage. So cathode rays emerge from the cathode and pass to the anode. But since the anode is containing holes, the cathode ray pass through it and move through a region of electric and magnetic fields and thus get deviated by some point. And here, as you can see, there is a fluorescent spot here which shows us at which position the cathode rays are hitting. Now, what will happen here is, if this is an electron, as we have proved that cathode rays are negatively charged particles and electrons, in the electric field, which is the dashed blue line, if we consider the electron to be in this region, then the force has to act in the outward direction. And in the magnetic field, if we use the same concept, then if I bring my pen here, okay, so it is moving in this direction, okay, it is moving in this direction, the magnetic field is in this direction, so let me cross it. So as you can see, I put my palm or my hand in the direction of V vector, I will curl the fingers in the direction B vector, the force vector should have been in this direction, but it is important to understand the charge for electron is negative. So it will be minus E into V cross B. So for whatever direction comes from the cross product, it has to be reversed. So in this part, if it is curling in this direction, the actual direction of force vector is in the opposite direction. Therefore, it is in the downward direction. Now what will happen here is, for the electric field, it is in the upward direction, like this, and then for for the magnetic field, okay, it is like in this direction, the electric field, and the magnetic field it is in this direction. So what J.J. Thomson did was, he adjusted the electric field and the magnetic field in such a way that these two are equal and opposite, and thus they cancel each other. Therefore, what will happen here is, this thing will move straight, and therefore for the straight travel, that is no deflection, both the forces have to be equal, so that there is no net acceleration. And when this we do Fm is equal to Fe, then we have E into V into B is equal to E into capital E, and thus we have here V is equal to E by B. So this is called the straight line travel velocity, which is E by B, or no deflection velocity. Now this is the main diagram that we have here. So first it was moving straight in this brown kind of a line, and we were moving in this direction. Now what happened here was, after J.J. Thomson did now that he turned off the magnetic field by turning off the electromagnets. So only electric field will start acting on this cathode ray tube or in this cathode ray. So what happened here was, now if only electric field is being applied, then the cathode ray will start to deflect to the positive plate because it is negatively charged. So as you can see that the fluorescent spot is above the midline, or the line it should have been. Therefore it moves by some distance x and it moves by some distance y. That is it moves by some distance x and also moves by some distance y, right? So if this is here is x and this is here is y, we can find x and y. So if we have a cross-sectional area of this, it would look something like this. What actually happening was here is that it is moving at the same velocity v, that is E by B. And now instead of having both electric and magnetic fields, the magnetic field is switched off and the electric field is applied. So now since the electric field is applied, it will move towards the positive electrode, and let the length of the positive electrode be L. The distance of the midpoint, like from where the particle is being thrown to the point, like to the electrode, the distance is S. And these are specified to us. S and L we have taken, and we have taken L in such a way that it hits the end point of L. So here we have V is equal to E by B, and we know X is equal to Vt, right? The X we were talking about here, X equal to Vt, and V we have E by B. So from here we will get time is equal to B by E into X. Similarly, using kinematic equation, we have Y is equal to half AT square. Now using force equation, because there is only one force acting on it, then there is Ma is equal to E into E. I have not taken the negative charge because I am not considering the direction, I am only considering the magnitude. So acceleration is equal to E by M into capital E, and thus we have, when we put all those things here, we have Y is equal to E by M into E into B by E into X whole square upon 2. And now this direction, as we can say, X is equal to L. Oh, sorry for that inconvenience. So now we have x equal to L and y is equal to S because we have taken these things like that. Therefore, S is equal to E by M into E into B by E into L whole square, and then we rearrange the terms in order to find this thing here. This thing here. We have E by M is equal to 2SE upon L square into H square. Now, I already told you that E and H is according to us. We can set the value of electric field intensity and magnetic field intensity. We can also set the value of the y direction. We can also set the value of the electrode, the size of the electrode and the distance between the electrode and the throwing point. So using these small values only, he could find the E by M ratio, and using several repeated experiments, he found the value of E by M ratio of 1.75880 into 10 to the power 11 coulomb per kg. So this is how we perform the experiment, which is a very basic experiment, and in case you have a cathode ray tube at your school or at your college or wherever you study, then you can perform this experiment, and this is a very basic kind of an experiment which normally is done in every college in case you are a physics student or a chemistry student. Normally it is not done as a chemistry student, but more for physics students do it a lot. But this pioneering experiment was the one that led us to discovery of electron and the E by M ratio of this electron. After this, how the charge and the mass came was a different story. The charge was discovered by R.M. Millikan using another experiment called the Millikan experiment, which will be discussed in one more Sciencation video. And I would like you to please like and subscribe to my channel. Like this video for more Sciencation videos. This here, as you can see, you will go to the one end of the corner to check out the video, the YouTube things that we like, and check out to the other corner for subscribing to my channel.